Time dilation is a fascinating concept from Albert Einstein's theory of special relativity. According to this theory, time does not flow at the same rate for everyone. Instead, it can speed up or slow down depending on the observer's speed and gravitational field. This means that two people may experience time differently if they are moving at different speeds or are in different gravitational fields. Imagine you and your friend are on a spaceship traveling near the speed of light. You might see time passing normally inside your spaceship, but if you look outside, you will notice clocks on Earth ticking slower. This is time dilation at work. Time dilation can be split into two main types, velocity-based and gravitational. Even though these ideas seem strange, they have been proven true with real experiments and observations. Understanding time dilation helps us grasp how our universe works. Velocity-based time dilation occurs when an object is moving very fast. The faster it moves, the slower time passes for it compared to someone standing still. This idea can be explained using the Lorentz factor, which is a formula that shows how much time slows down. The Lorentz factor is given by the formula. Text, Lorentz factor, =frac 1, sqrt 1, frac v 2 is c squared. As the velocity v approaches the speed of light, the Lorentz factor increases, meaning time slows down more and more. Imagine an astronaut, Anna, on a spaceship traveling at 90% of the speed of light. If she looks at a clock on Earth, she would see it ticking slower than her clock inside the spaceship. Anna ages slower than her friends on Earth because time is passing slower for her. This concept is not just science fiction. It has been confirmed through experiments with particles traveling at high speeds. Even though we don't travel near the speed of light in everyday life, this effect becomes significant in high-speed scenarios. Gravitational time dilation happens due to gravity's influence on time. In strong gravitational fields, time ticks slower compared to weaker fields. This idea can be explained with the formula from general relativity to t^{1, frac 2gm rc squared. Consider a black hole, which has an extremely strong gravitational field. If you were to approach a black hole, you would notice that time for you slows down compared to someone far from it. This means you could experience just minutes while years pass for others far away from the black hole. Gravitational time dilation has been observed with clocks placed at different altitudes on Earth. Clocks at higher altitudes where gravity is weaker tick slightly faster than those at sea level. GPS satellites provide a real-world example of both types of time dilation. These satellites orbit Earth at high speeds and are also further from Earth's gravity compared to us on the surface. This means they experience both velocity-based and gravitational time dilation. For GPS to work accurately, time dilation effects must be corrected. The onboard clocks tick faster because they are higher up, away from Earth's strong gravity. They also tick slower due to their speed. Without correcting these differences, GPS would become inaccurate, leading to incorrect positioning by several kilometers. Length contraction is another strange effect from special relativity. It states that objects moving at high speeds will appear shorter in the direction of motion to a stationary observer. The formula for length contraction is L equals L, naught times the square root of 1 minus v squared over c squared. The barn paradox is a thought experiment demonstrating frame dependency. Imagine a pole vaulter running with a pole that fits just inside a barn when stationary. But when running fast near light speed, the pole contracts, fitting entirely inside the barn for a moment. From the vaulter's view, the barn is contracted, and the pole never fully fits inside. Both perspectives are correct, showcasing how different frames of reference can change observations. Time and space are not as rigid as they seem. Both can stretch and bend when influenced by speed and gravity, as shown in time dilation and length contraction. These concepts may seem complex, but they are fundamental to understanding our universe. They highlight how observers moving at different speeds or in varying gravitational fields can have unique experiences of time and space. From astronauts aging slower to GPS satellites requiring time adjustments, relativity's effects are all around us. Even though we might not notice these effects in our daily lives, they are real and have been proven by many experiments. These ideas challenge our perceptions but open a window into the true nature of our universe. By embracing these concepts, we can appreciate the wonders of the cosmos and the cleverness of human understanding.